Imagine for a second that you've just pulled off one of the most profound intellectual feats in the history of human civilization.
Right. Not just, a small incremental update to a textbook or something.
Exactly. You haven't just tweaked a theory. You have quite literally looked up at the night sky, pored over the data, crunched, just an incomprehensible amount of numbers, and figured out what the entire universe is made of.
Which should be a moment of pure, unadulterated triumph. I mean, you hold the blueprint of the cosmos right there in your hands.
Yeah, it should be the greatest day of your life. But then you take your findings to the top expert in your field, like the absolute most respected mind of the day, the ultimate gatekeeper.
Yeah.
And he looks at your definitive, mathematically sound results, and he tells you that it's impossible.
He tells you it must be wrong simply because it contradicts what everybody else already, quote-unquote, knows to be true.
Right. And because of the immense power dynamics at play, you're forced into this agonizing position. You have to write in your own groundbreaking doctoral thesis that your results, these incredibly accurate calculations that you know in your bones are correct, are, and I quote, almost certainly not real.
You have to publicly doubt your own genius just to get your degree. It's the ultimate nightmare scenario for any researcher.
It's so infuriating, but here's where this historical reality goes from tragic to just absolutely maddening. 4 years later, that exact same expert who told you that you were wrong, the guy who forced you to retract your findings, he publishes your exact findings.
Yeah, he proves that you were right all along.
And because he's the established authority, he basically gets the primary credit for the discovery.
It is a staggering historical contradiction. And it perfectly encapsulates, the immense friction that happens when a revolutionary idea collides with comfortable, established dogma. The establishment rarely just surrenders its worldview without a fight, even when the math is staring them right in the face.
Today's deep dive is about the person who lived that exact infuriating nightmare. We are exploring the life, the brilliant mind, and the, well, just immeasurable legacy of Cecilia Payne-Gaposchkin.
Born in 1900, died in 1979. She was a British-born American astronomer and astrophysicist who fundamentally shifted human understanding of the cosmos.
Our mission today is to track her incredible journey. We're going to unpack the actual science of how she proved that stars are primarily made of hydrogen and helium, and we'll examine the crushing systemic barriers she navigated at Harvard University.
And crucially, we'll see how her quiet, relentless persistence ultimately shattered the glass ceiling for women in astrophysics.
Yeah. And while the story of that delayed credit is a profound example of institutional barriers, it's really critical to view this not just as a story of prejudice, right?
Absolutely not. It is a profound lesson in the danger of scientific consensus. It forces us to look at how the scientific method actually operates in the real world, where human egos, ingrained assumptions, and collective blind spots can obscure the truth for years.
Sometimes decades. So before Cecilia Payne-Gaposchkin was, analyzing the cosmos and rewriting the elemental rules of the universe, she was a young girl growing up in England, developing a fiercely independent mind. Let's start right there.
She was born Cecilia Helena Payne on May 10th, 1900, in Wendover, Buckinghamshire. She came from a very erudite Prussian family.
Right. Her mother was Emma Leonora Helena Pertz, and her father, Edward John Payne, was a London barrister, a historian, and a musician who had been an Oxford Fellow.
It was a family deeply entrenched in intellectual pursuits. Just to give you an idea of the lineage, she had two very distinguished great-uncles, the historian Georg Heinrich Pertz and the Swedenborgian writer James John Garth Wilkinson.
So she's born into this environment where rigorous intellectual pursuit is basically the family business. There was an expectation of curiosity.
But that environment gets disrupted very early on. Her father dies when she's only 4 years old, leaving her mother to raise 3 children entirely on her own.
And despite this rich intellectual heritage on both sides of her family, Cecilia's early education was incredibly restricted. She started at a private school in Wendover, but when she was 12, the family packed up and moved to London.
And the reason to this move is quite telling. They relocated specifically to facilitate the education of her brother, Humphrey.
Right. Who would actually go on to become a notable archaeologist.
Exactly. Cecilia, meanwhile, gets sent to St. Mary's College in Paddington. And from what I understand from our sources, studying mathematics or science wasn't even really an option for her at this school.
Yeah, the educational infrastructure of early 20th century England was explicitly designed to funnel young men into the sciences and leadership roles, while young women were directed toward more domestic or artistic pursuits.
Her brother's classical education was viewed as an absolute priority, which necessitated the move to London. Cecilia's scientific curiosity was essentially structurally starved at St. Mary's. The institution simply didn't possess the curriculum, or really the inclination, to teach a young woman advanced mathematics.
I want to pause on that because it sets up a dynamic we're going to see play out for her entire life. The world is constantly telling her, hey, this specific door is not for you. But she just keeps finding other doors.
She always finds another way.
Yeah. In 1918, she manages to transfer to St. Paul's Girls' School, and she crosses paths with a very famous music teacher there, the legendary composer Gustav Holst.
Right. Holst looks at Cecilia's talents and strongly encourages her to pursue a career in music. He saw genuine potential in her.
And Holst was a towering figure in British music, best known for his orchestral suite, The Planets.
Having a figure of his magnitude take a personal interest in your artistic development, I mean, that was the kind of endorsement that could guarantee a comfortable, highly respected career.
Right. It's like having Gordon Ramsay tell you that you're a phenomenal chef and offering you the head job at his new restaurant, but you look him in the eye and say, no thanks, I'm going to go map an uncharted jungle by myself.
That's a great analogy. She deliberately turns down a path in music, endorsed by a musical titan, because she is utterly compelled to focus on science.
It highlights this profound internal compass. She wasn't seeking prestige, and she wasn't seeking the approval of authority figures. She was seeking the fundamental truth of how the natural world worked.
The comfort of a musical career under Holst's patronage was, infinitely less appealing to her than the grueling, uncertain pursuit of scientific discovery.
And we see this exact same empirical mindset completely override her religious upbringing during her school years as well. Oh, this is the story about her school exams. I read this in our notes and it completely blew my mind. Walk us through what she did.
So in her autobiography, which she later published under the title The Dyer's Hand, she recounts this experiment she designed while she was a young student. She wanted to test the actual measurable efficacy of prayer.
I love this so much.
Right. So she took her school exams and divided them into two separate groups. One was the test group, and the other was a scientific control group. She prayed fervently for success on the test group of exams, and she actively, consciously refrained from praying about the control group.
She basically ran a double-blind clinical trial on the existence of divine intervention. As a teenager,
She applied the scientific method to theology and the results of her experiment. She achieved higher marks in the unprayed-for control group.
no way.
Yes. So based on that empirical data, she concluded that prayer did not yield measurable results. She abandoned her religious upbringing and became a devout agnostic for the rest of her life.
That tells us exactly who we're dealing with. I mean, if she is willing to look up at the heavens as a teenager, run the numbers on God, and adjust her entire worldview based on the data, she is absolutely not going to back down when a human astronomer tells her her math is wrong.
That is the critical takeaway here. This is a brain hardwired for empirical data over authority. If the data says one thing and tradition says another, she follows the data, period.
It's the exact psychological trait she's going to need when she eventually faces down the entire astronomical establishment. So we have this fiercely independent, data-driven young woman who has just won a scholarship to Newnham College at Cambridge University in 1919. She's studying physics and chemistry.
And this brings us to a specific night that essentially acts as the inciting incident for the rest of her life, the lecture by Arthur Eddington.
Set the stage for us. Who is Eddington, and what is he talking about that night in 1919?
Arthur Eddington was a highly prominent British astronomer, physicist, and mathematician. In 1919, he had just returned from a famous expedition to the island of Principe, which is off the west coast of Africa. His goal on that expedition was to observe and photograph a total solar eclipse.
Okay, but he wasn't just taking pictures for the sake of it, right?
No, not at all. He was attempting to test Albert Einstein's relatively new, highly controversial general theory of relativity.
Why an eclipse, though? Like, how does a solar eclipse test relativity?
Well, up until this point, Isaac Newton's view of the universe was absolute law. Gravity was viewed as a straightforward pulling force between objects.
Yeah.
But Einstein had proposed something radical, that massive objects, like the sun, actually warp the fabric of space-time around them.
So think of a bowling ball sitting in the middle of a trampoline.
Exactly. If Einstein was right, the light from distant stars traveling past the sun would have to follow the curve of that warped space-time. The light would literally bend.
But you normally can't see stars right next to the sun because, well, the sun is too bright.
Right. Hence the total solar eclipse. When the moon blocks the sun's blinding light, You can briefly see the stars in the background right near the edge of the sun. Eddington photographed those stars during the eclipse and then compared their positions to photographs taken of the same stars at night 6 months later when the sun was nowhere near them.
And what did he find?
The photographs from Principe proved that the stars appeared to have shifted position. Their light had bent around the sun's mass. It was the first empirical proof of Einstein's theory. It was a paradigm-shattering moment for physics. It proved that the universe operated on rules entirely different from what humanity had assumed for centuries.
And Cecilia Payne is sitting in the audience at Cambridge, listening to Eddington present these findings. Her reaction to hearing this was so intense that she described it in her own words as a complete transformation of her world picture. She actually said, "My world had been so shaken that I experienced something very like a nervous breakdown."
Think about the intellectual whiplash of that moment for someone like her. She is someone who craves absolute empirical truth. She sits in a room and watches a man present photographic data that completely rewrites the fundamental laws of gravity, space, and time.
Yeah, it wasn't just an interesting academic lecture for her, it was an existential awakening.
It was the realization that the universe was vastly more complex, dynamic, and discoverable than anyone had previously thought. The curtain had been pulled back, and she realized the true nature of reality was waiting to be decoded. That is the moment her focus shifts irrevocably toward astronomy.
But as she pivots her brilliant mind toward this new frontier, she hits a brick wall. And I want you, the listener, to really internalize the timeline here. She does the grueling work. She completes her studies in physics and chemistry at Cambridge. But Cambridge University refuses to grant her an official degree.
Because she is a woman.
And I want to emphasize this. Cambridge wouldn't officially grant degrees to women until 1948.
The cruelty of the bureaucracy is just staggering. You have a mind capable of grasping the profound nuances of general relativity and quantum physics, and the institution's response is essentially, "Thank you for completing the coursework, but you cannot be credentialed. You cannot officially exist as a scholar here."
I really want you to think about that year for a second. 1948. We aren't talking about the Middle Ages here. We are talking about the era of nuclear energy, radar, and jet planes. And one of the most prestigious academic institutions on the planet still wouldn't hand a piece of paper to a woman who had passed their own rigorous exams.
It meant she had no future in British academia. Because she didn't have a formal degree, her only viable career path in the UK was to become a secondary school teacher.
Imagine experiencing a scientific nervous breakdown because you've just seen the literal fabric of space-time explained, and then being told that your absolute ceiling in life is grading high school science quizzes in a local village.
It was an unacceptable reality for her. She knew the structural dams holding her back in the UK were insurmountable. If she wanted to actually practice science, to be on the frontier of discovery, she had to leave the country.
So she begins searching for grants and fellowships that would enable her to move to the United States. And this leads to her escape. She attends a lecture in London at the British Astronomical Association, and she meets a Cambridge PhD student named Leslie Comrie.
Comrie recognizes her talent and introduces her to a man named Harlow Shapley, who is the newly appointed director of the Harvard College Observatory in Massachusetts.
And Shapley offers her a lifeline. He secures her a fellowship to move to the U.S. in 1923 to study at the Harvard Observatory.
The Harvard College Observatory is a really fascinating piece of this puzzle. We need to look at why Shapley was open to bringing a brilliant young woman across the Atlantic in the first place. Shapley wasn't operating in the vacuum. He was running an observatory that possessed a very unique, albeit deeply complicated, history of utilizing female talent.
Right.
Decades earlier, under a previous director named Edward Charles Pickering, the observatory had employed a group of women who became known as the Harvard Computers.
Oh, I've heard of them. Women like Williamina Fleming, Antonia Maury, Annie Jump Cannon, and Henrietta Swan Leavitt.
Yes. In the late 1800s and early 1900s, the observatory was collecting thousands of photographic glass plates of the night sky. Analyzing these plates, cataloging the stars, measuring their brightness, identifying their spectra, it was incredibly tedious, painstaking work. Pickering hired women to do this analysis.
But from what I understand, Pickering didn't hire them because he was some progressive feminist champion. He hired them because women could be paid a fraction of what men demanded. It was essentially cheap, highly skilled labor. It was exploitative.
It was absolutely exploitative. They were paid essentially clerical wages for doing complex astronomical data analysis. But, inadvertently, Pickering created a space where women could actually touch raw astronomical data. These women weren't just transcribing numbers, they were making massive discoveries.
Like Henrietta Swan Leavitt, right?
Exactly. For instance, she discovered the relationship between the luminosity and the period of Cepheid variable stars, which literally provided the yardstick that allowed astronomers to measure the distance to other galaxies.
So despite the exploitative origins, the legacy of the Harvard computers meant that the observatory already possessed an infrastructure and a culture of women working in astronomy. It offered more opportunities to women than almost any other institution in the world.
Precisely. When Harlow Shapley took over as director, he inherited and continued this tradition. In 1922, a woman named Adelaide Ames was the first recipient of a newly established fellowship designed to encourage women to study at the observatory. Cecilia Payne followed as the second recipient of that fellowship in 1923.
So she packs her bags, crosses the Atlantic, and arrives in Cambridge, Massachusetts. Lawrence H. Aller, another astronomer, later described her as one of the most capable go-getters in Shapley's observatory. She just dives into the work.
She takes related courses through Radcliffe College, which was the women's college affiliated with Harvard, since Harvard proper still refused to grant doctorates to women.
And Shapley, recognizing her sheer brilliance, persuades her to write a doctoral dissertation.
He directs her immense analytical power toward a massive archive of data that the observatory had been collecting for decades, the stellar spectra.
Which sets the stage for her 1925 thesis, a document that astronomer Otto Struve would later explicitly call the most brilliant PhD thesis ever written in astronomy. The title of the thesis is a mouthful. It's called Stellar Atmospheres, a contribution to the observational study of high temperature in the reversing layers of stars.
Let's translate that into plain English.
Yes, please. What was she actually looking at every day in the observatory?
She was looking at photographic glass plates. To understand what she did, we have to understand the mechanics of spectroscopy. If you take the light from a star and pass it through a prism, that light spreads out into a rainbow of colors, a spectrum.
Okay, got it.
But if you look very closely at that rainbow, it isn't a perfectly continuous smear of color. There are tiny, distinct, dark, vertical gaps or lines interrupting the rainbow. These are known as absorption lines.
Wait, let me make sure I'm visualizing this correctly. Why are there dark lines missing from the rainbow? Where does the light go?
It has to do with the atmosphere of the star itself. A star has a burning core that produces light, but that light has to travel outward through the cooler, outer gaseous atmosphere of the star before it journeys across space to reach our telescopes. The chemical elements present in that outer atmosphere act like a filter.
Oh, interesting.
Every specific chemical element, iron, carbon, silicon, calcium, hydrogen, absorbs light at very specific, unique wavelengths.
I always like to think of a star's light spectrum like a barcode on a product of a grocery store. As the light travels through the star's atmosphere, the elements in that atmosphere absorb their specific colors, effectively removing those wavelengths from the light that reaches Earth.
That's a great way to picture it.
That leaves dark lines in the spectrum. So by reading the barcode, by looking at exactly where the dark lines fall, astronomers can tell exactly what elements are floating in the atmosphere of that star.
The barcode analogy is excellent. So the Harvard Observatory had collected thousands of these barcodes on photographic glass plates. Before Cecilia Payne began her thesis, astronomers had been looking at these barcodes from thousands of different stars, and they were profoundly puzzled.
Why?
The barcodes were vastly different from star to star. Some stars had huge, thick lines indicating massive amounts of calcium or iron. Other stars had totally different barcode patterns with almost no calcium lines.
So the logical assumption, which became the established dogma of the day, was that stars must be made of vastly different materials.
Exactly. The scientific consensus was that stars were as chemically diverse as the planets. They assumed some were iron stars, some were calcium stars, and furthermore, they believed that if you took the overall average composition of all these stars, it would essentially mirror the composition of the Earth's crust.
Wait, really?
Yeah, they believed the universe was essentially uniform in its makeup, a bunch of rocky, metallic material just heated up to massive temperatures.
They thought the universe was just glowing hot Earth dirt.
Essentially, yes. But Cecilia Payne looked at this massive variation in the stellar absorption lines and realized something was missing. She applied a brand new, cutting-edge concept called ionization theory, which had just been developed by an Indian physicist named Meghnad Saha.
Okay, slow down here, because this is the crux of the genius. What does Saha's ionization theory actually explain? How does it change the way she looks at these barcodes?
Ionization theory explains how extreme heat affects the structure of an atom. An atom consists of a nucleus surrounded by a cloud of orbiting electrons. If you apply heat to that atom, the electrons get excited and jump to wider orbits. But if you apply enough intense heat, stellar levels of heat, the electrons actually get violently stripped away from the nucleus entirely. That process is called ionization.
Okay, so the star is so hot it's literally ripping the electrons off the atoms. How does that affect the light we see?
Because an atom's ability to absorb specific wavelengths of light, its ability to create that specific dark line in the barcode depends entirely on the arrangement of its electrons. Saha's theory provided a mathematical equation to calculate exactly how many electrons would be stripped away from different chemical elements at different specific temperatures.
I see. So if the electrons are ripped away by the heat, the atom can no longer absorb the light. The barcode line vanishes.
Yes. She realized that the barcode scanner, the way we read the light, changes depending on how hot the star is. She realized that if a star lacked the barcode lines for calcium, it absolutely did not mean the star lacked calcium.
Right.
It just meant the star was burning at such an incredibly high temperature that all the calcium atoms had been completely ionized. Their electrons were gone, meaning they were physically incapable of absorbing light to produce that specific line in the barcode. The calcium was still there. The extreme heat was just making it invisible to our instruments.
That is staggering. So the massive, confusing variations in all these stars wasn't because they were made of different elements. It was simply because they were all burning at wildly different temperatures.
Precisely.
It's like looking at a block of ice, a glass of water, and a cloud of invisible steam and concluding that they are three completely different chemicals when really they're all just H2O existing at different temperatures.
It was a monumental paradigm-shifting breakthrough. She used Saha's complex equations to mathematically strip away the temperature distortions from the data. She corrected for the heat. And when she did that, she found something that completely upended human understanding of the cosmos.
What did she find?
First, she found that the heavier elements like silicon, carbon, and the common metals we see on Earth were indeed present in stars in roughly the same relative proportions as they are on Earth.
Which the establishment would have loved because it confirmed their Earth crust theory.
Right. But then she calculated the absolute abundance of the lighter elements, specifically helium and hydrogen, and the numbers broke the scale. She discovered that hydrogen wasn't just present, it was vastly, overwhelmingly more abundant than anything else. Her calculations showed that hydrogen was roughly 1,000,000 times more prevalent than the heavier elements.
1,000,000 times. That completely shatters the entire worldview of astronomy. The universe isn't a bunch of hot rocks. The universe is essentially a giant, swirling ocean of hydrogen gas.
She proved that hydrogen is the overwhelming constituent of stars, making it the fundamental building block of the entire universe. Today, modern astrophysics confirms that the observable universe is roughly 74% hydrogen and 24% helium by mass, with all the other heavier elements making up just a tiny 2% fraction.
Wow.
Cecilia Payne's 1925 calculations, done with glass plates and handwritten math, were perfectly aligned with this modern understanding. She nailed the fundamental composition of reality.
You make a discovery like that, you have the mathematical proof. You have solved the puzzle of the stars. You expect a parade. You expect the Nobel Prize, the cover of every scientific journal. Instead, she hits a brick wall of scientific consensus. And this brings us to the tragedy of Henry Norris Russell.
Henry Norris Russell was a titan. He was the preeminent, most highly respected astronomer in America at the time. He was the director of the Princeton University Observatory, and crucially, he was acting as a primary reviewer and advisor for her doctoral dissertation.
So why does he reject her findings? Is he just jealous?
It's more complicated than that, and it speaks to the nature of scientific dogma. Russell was deeply committed to a theory proposed earlier by an American physicist named Henry Rowland. Rowland's theory was the foundation of the hot rock universe we discussed.
Okay, great.
Rowland stated that if the Earth's crust were heated to the temperature of the sun's atmosphere, their absorption spectra would look identical. Therefore, the sun must be made of the exact same stuff in the exact same proportions as the Earth. In a prominent 1914 article, Russell had explicitly argued and published that the relative abundance of elements in the universe matched the Earth's crust.
So Russell is the ultimate gatekeeper. He reads Payne's thesis, he sees her brilliant application of Saha's ionization theory, and he accepts her findings regarding the heavier metals because they don't challenge his worldview. But when he looks at the staggering astronomical numbers for hydrogen and helium, he balks.
He cannot reconcile an entire universe made of hydrogen with the established physics he has spent his life defending. He writes to her and tells her that her conclusion about the sheer abundance of hydrogen is, and this is the specific word he used, spurious.
Spurious, meaning false, fake, illegitimate. He completely rejects the most important scientific discovery of the century because it doesn't match his own previously published theories. I get genuinely fired up about this. It's so easy to paint him as a cartoon villain protecting his ego.
It is deeply frustrating. But if we analyze it objectively, this highlights how science is inherently structurally conservative. When a paradigm has been established and supported by the leading minds for decades, a single paper overturning it, especially a paper written by a female graduate student, is going to face immense resistance.
Yeah, I guess so.
Russell genuinely believed the data must be flawed because the conclusion was too radical. He thought there must be an error in how the ionization equations applied to hydrogen at those extremes.
But the tragedy isn't just that he doubted her. The tragedy is what his power forced her to do. She is a graduate student. She is a woman in a field totally dominated by men. She has no formal degree from Cambridge. She desperately needs this Harvard PhD to survive academically. She cannot afford to go to war with the most powerful astronomer in America.
Right.
So, under immense systemic pressure, Payne caves. She accommodates his criticism to get her degree approved.
She alters the text of her own thesis. She adds a statement regarding the staggering calculated abundance of hydrogen and helium, writing that these results are almost certainly not real, and suggesting they are likely an artifact of stellar conditions we don't yet understand.
Almost certainly not real.
Yeah.
It is deeply painful to read. She had the literal truth of the universe in her hands, and the system forced her to publicly disavow it. But she gets the degree. She becomes the first person to earn a PhD in astronomy from Radcliffe College.
And then the ultimate insult occurs. 4 years later, in 1929, the established dogma begins to crack. Henry Norris Russell conducts his own independent research using slightly different means and newer data, and he derives the exact same results regarding hydrogen.
Of course he does.
He realizes the math is undeniable. He realizes that Cecilia Payne had been right all along. He effectively demonstrates that hydrogen and helium are the most abundant elements in the Sun and the Milky Way. And he publishes a massive paper on it.
Now, I want to be historically precise here. Russell didn't just steal her paper in the dead of night. He did briefly acknowledge her earlier work in his 1929 publication.
Yes, he wrote, "The most important previous determination of the abundance of the elements by astrophysical means is that by Miss Payne."
A passing citation. Oh, by the way, Miss Payne determined this 4 years ago, but anyway, here is my definitive authoritative paper on it. And because he was Henry Norris Russell, because he possessed the institutional authority, the gender, and the prestige that she lacked, the scientific establishment accepted the hydrogen universe immediately.
Exactly. And he was generally credited for the conclusions that she had mathematically proven 4 years prior.
It is the starkest possible example of how systemic bias operates in intellectual spaces. When a marginalized voice speaks a revolutionary truth, it is deemed spurious. When a powerful, established voice repeats the exact same truth, it instantly becomes established scientific fact. How do you bounce back from that?
It's hard to imagine.
How do you wake up the next morning and keep going to the observatory when your crowning achievement, the literal composition of the stars, is credited to the man who forced you to retract it? If it were me, I might have walked away from academia entirely in disgust.
But she didn't walk away. She stayed at Harvard. And she responded to the theft of her legacy by simply outworking every single person around her. She chose the long game. She knew that undeniable, overwhelming foundational data was the only way to build a legacy that couldn't be erased or co-opted.
This begins a period of her life that lasted for decades, from the 1930s all the way through the 1950s, which we can only describe as grinding in the shadows. Because she was a woman, she was explicitly barred from becoming a professor at Harvard, so she spent decades relegated to doing less prestigious, terribly paid research.
Her official titles during this period were essentially administrative insults. Harlow Shapley, the director who brought her over, tried to help her navigate the bureaucracy. In 1938, he finally managed to get her the official title of astronomer. But to get that approved by the university brass, Shapley had to explicitly assure the president of Harvard that giving her this title would not make her equivalent to a professor.
Later on, she asked to be called the Phillips astronomer, which was an endowed position. Shapley pushed privately to make it a true professorship, but the institution fiercely resisted. To give you an idea of how invisible they made her, she was teaching courses to graduate students. But those courses weren't even recorded as officially available in the Harvard University catalog until 1945.
It's the academic equivalent of being a ghost. You are doing the foundational research. You are actively training the next generation of astrophysicists. but the institution structurally refuses to put your name on the door.
Despite this suffocating environment, the sheer volume of work she produced during this time is difficult to comprehend. What was she actually studying while stuck in this low-paid limbo?
Her early postdoctoral work focused on stars of high luminosity, culminating in a 1930 book called The Stars of High Luminosity. But her true magnum opus during this grinding, decades-long period was her work on variable stars.
Break that down for us. Variable stars are stars whose brightness fluctuates over time, right? They aren't a steady light bulb, they pulse.
Exactly, they pulsate, getting brighter and dimmer in measurable cycles. By tracking the timing and intensity of these changes, astronomers can calculate incredible amounts of vital information about the star, its absolute distance from Earth, its mass, and where it is in its evolutionary life cycle. Payne decided to survey all stars brighter than the 10th magnitude. And she didn't just look at a handful to establish a theory. Working alongside her assistants, she made more than 1.25 million individual observations of variable stars.
Let me stop you there. 1.25 million observations. How do you physically do that without modern computers or digital imaging?
It is entirely manual labor. You are pulling individual, fragile photographic glass plates from the archives. You are placing them under a magnifying loupe or a specialized microscope. You are visually identifying a specific speck of light among thousands of others.
Sound exhausting.
It is. You are comparing the size and density of that dark speck to reference stars on the same plate to estimate its magnitude. You write that number down in a logbook, then you pull another plate of the exact same star taken days or weeks later, find the dot again, measure it again, log it again. You do this to track the change over time. Now repeat that physical, eye-straining process 1.25 million times.
It is a level of monastic devotion to the data. And she didn't stop there.
No. She later extended this work to the Magellanic Clouds, which are two irregular dwarf galaxies visible from the southern hemisphere. That project added a further 2 million observations.
Over 3 million observations. Just pure, relentless, unglamorous data gathering. And this wasn't just busy work to keep her occupied while the men did the real theoretical physics, was it?
Not at all. Her massive data sets and her brilliant analysis of that data laid the literal foundation for all subsequent work on stellar evolution. She essentially mapped out how stars are born, how they age, and how they die.
That's incredible.
She published these sweeping findings in her 1938 book, Variable Stars, and later in her 1954 book, Variable Stars and Galactic Structure. She became the undisputed global authority on the life cycle of the galaxy.
What I find most amazing about this era of her life is how tightly integrated her personal life was with this grueling scientific work. In 1933, she is on a tour through Europe, attending astronomical meetings, and she meets a Russian-born astrophysicist named Sergei Ilarionovich Gaposchkin in Germany.
Right. Sergei had lost his position due to the political turmoil in Europe. She helps him obtain a visa to come to the United States. He arrives, and they get married in March 1934. She adds his name to hers, becoming Cecilia Payne-Gaposchkin.
And Sergei becomes her closest, most dedicated collaborator. Those 3 million variable star observations we just talked about, they carried out a vast majority of that work together as a team. It was a remarkable scientific and romantic partnership.
They also had 3 children together, Edward, Catherine, and Peter. And the way she balanced this domestic reality with her astronomical output is mind-blowing. During the World War II years, normal scientific work at the Harvard Observatory was severely disrupted. Staff went off to the war effort, resources were scarce.
But Cecilia and Sergei just kept grinding.
They practically lived at the observatory, often taking their kids with them to work among the telescopes and the stacks of glass plates. They lived in Lexington, Massachusetts. But to survive the wartime rationing and shortages, they also maintained a small farm near Townsend, where they raised pigs and poultry, delivering meat and eggs to local markets themselves.
Her daughter later remembered her as an inspired seamstress, an inventive knitter, and a voracious reader of literature. She was teaching Sunday school at the First Unitarian Church in Lexington. She was active with the Quakers. She was farming pigs. She was raising 3 children. And in her spare time, she was casually cataloging millions of stars to map the structural evolution of the galaxy.
The sheer capacity of her mind and her physical stamina is almost difficult to comprehend.
And it seems her passion for science was deeply contagious in that household, because all 3 of her children ended up becoming scientists themselves. Catherine and Peter became astronomers, and Edward became a computer scientist and geologist. She was raising the next generation of scientists at her dining room table.
It speaks to the environment of relentless curiosity and resilience she fostered. But back in the professional realm at Harvard, the sheer weight of her contributions, her foundational books, her millions of observations, her undeniable status as a global expert was slowly, inevitably building up against the structural dams that were holding her back. The institution could only ignore a titan for so long.
Eventually, the dam breaks. It takes decades, but in 1954, a man named Donald Menzel takes over as the director of the Harvard College Observatory, replacing Harlow Shapley. And Menzel looks at the situation and actively decides to rectify this historical embarrassment. He pushes the university to improve her appointment.
Menzel recognized the sheer absurdity of having one of the world's greatest living astrophysicists relegated to a lesser unofficial title simply because of her gender. In 1956, the breakthrough finally happens. Harvard University relents. She's officially promoted to full professor.
She becomes the first woman to be promoted to full professor from within Harvard's Faculty of Arts and Sciences. That is a massive historical milestone for the university. And her ascent didn't stop there. In 1958, she was appointed the Phillips Professor of Astronomy. And eventually, she was appointed as the chair of the Department of Astronomy. That made her the first woman to ever head a department at Harvard University.
The historical significance of this cannot be overstated. With her PhD in 1925, she proved that women could do the absolute highest level of theoretical astrophysics. But with her promotion to full professor and department chair in 1956, women officially entered the mainstream of academic power at one of the world's most prestigious and traditionally gate-kept institutions.
She didn't just walk through the door, she tore it off the hinges so other women could follow.
And she spent a huge amount of her time mentoring that next generation. Her list of students reads like a who's who of 20th century astronomy. She supervised Frank Drake, the pioneer of the search for extraterrestrial intelligence. She supervised Owen Gingerich. She mentored people like Joseph Ashbrook, Harlan Smith, and Paul W. Hodge.
And crucially, she supervised Helen Sawyer Hogg, who went on to become an absolute titan in astronomy herself, discovering thousands of variable stars in globular clusters.
Her output simply never stopped. She edited and published the lectures of Walter Bade into a highly influential book called Evolution of Stars and Galaxies in 1963. Even after she officially retired from active teaching in 1966 and was named Professor Emerita, she kept researching as a staff member at the Smithsonian Astrophysical Observatory. She edited Harvard Observatory journals for another 10 years.
But the most touching part of her legacy, the part that really resonates with me, isn't just the famous students she directly taught in a classroom. It is the invisible, rippling impact of her mere existence in the scientific record. There is a specific story in the sources about an astrophysicist named Joan Feynman, who was the sister of the famous physicist Richard Feynman, that illustrates this perfectly.
It is a beautiful example of the power of representation. Joan Feynman was a brilliant young woman with a deep passion for the natural world, but she was actively, forcefully dissuaded from pursuing science by her own mother and grandmother. They explicitly told her that women were not physically capable of understanding complex scientific concepts.
Wow.
They believed, based on the societal norms of the time, that the female brain simply wasn't built to handle the rigorous math and physics required for astronomy.
Imagine hearing that from the people closest to you. You have this burning curiosity about how the universe works, and your own family tells you that your biology makes it impossible. That is the kind of discouragement that extinguishes brilliance before it even starts.
But then, Joan Feynman is looking through an astronomy textbook, and she comes across a chart detailing the complex absorption lines of stellar spectra. The text accompanying the chart cites the foundational research of one Cecilia Payne-Gaposchkin. Joan looked at the name, did a little digging, and realized it was a woman.
Oh, that's amazing.
She saw Cecilia's name and her definitive, mathematically rigorous data printed in a textbook as established scientific fact.
And in that moment, Joan Feynman realizes her mother and grandmother were completely wrong. The societal lie shatters. Cecilia Payne's mere existence in print, her name attached to undeniable data, gave Joan Feynman the silent permission to pursue her passion. Joan saw that a woman had not only understood these concepts, but had literally written the foundational rules of them.
And because of that, Joan Feynman ignored her family's warnings and went on to have a brilliant, highly influential career in astrophysics, making major contributions to the study of auroras and the solar wind.
If we extrapolate the broader implications of that single story, how many Joan Feynmans are out there because Cecilia Payne-Gaposchkin refused to quit? By simply surviving in a space where she was structurally unwelcome, by enduring the stolen credit of her thesis, the low pay, the grueling manual labor, and the insulting administrative titles, she created a beacon for every woman who came after her.
It's one thing to make a brilliant discovery. It's an entirely different level of legacy to be a living proof of concept for an entire marginalized group.
And she did eventually receive numerous institutional honors recognizing this, though many came late in her life. She was elected to the American Philosophical Society in 1936 and the American Academy of Arts and Sciences in 1943. She won the Award of Merit from Radcliffe College in 1952 and the Rittenhouse Medal from the Rittenhouse Astronomical Society in 1961.
And perhaps most poetically, she was the first ever recipient of the American Astronomical Society's Annie Jump Cannon Award in astronomy back in 1934, named after one of the original Harvard computers whose legacy she built upon.
But the award that stands out the most is the one she received in 1976. In a massive full-circle moment of ultimate historical irony, she was awarded the Henry Norris Russell Prize by the American Astronomical Society. Yes, the ultimate lifetime achievement award in her field was named after the very man who, 50 years earlier, had dismissed her brilliant thesis on hydrogen as spurious and forced her to retract the greatest discovery of her life.
It is the ultimate vindication. But what is truly remarkable is her acceptance speech for that prize. She didn't use the moment for bitterness or vindictive triumph. She used it to reflect on the pure intrinsic value of scientific discovery. She said, and I quote, "The reward of the young scientist is the emotional thrill of being the first person in the history of the world to see something or understand something. Nothing can compare with that experience. The reward of the old scientist is the sense of having seen a vague sketch grow into a masterly landscape."
A vague sketch grow into a masterly landscape. That is exactly what she did with her life's work. She looked at the confusing, chaotic, misunderstood barcodes of the stars, and she painted the definitive picture of a universe made of hydrogen and helium.
She died in Cambridge, Massachusetts on December 7, 1979, at the age of 79. But her name literally lives on in the cosmos she spent her life studying. There's an asteroid floating out there in the solar system named 2039 Payne-Gaposchkin, which was discovered in 1974.
That's fitting.
There's even a volcano on the surface of Venus, the Payne-Gaposchkin patera, bearing her name. The Institute of Physics named a medal in her honor, and the American Physical Society renamed their doctoral dissertation award in astrophysics after her, ensuring her name is forever linked to the most brilliant young minds entering the field.
Let's look back at the sheer scale of the arc we just traced. She started as a fatherless girl in Wendover, England, running empirical prayer experiments on her school exams because she trusted data over dogma. She grew into a fiercely independent mind whose worldview was shattered by the physics of relativity.
She fled a country that wouldn't give her a degree, landed at Harvard, applied quantum mechanics to starlight, and deciphered the elemental composition of the universe.
She was told she was wrong by the gatekeepers of the establishment, forced to doubt her own genius, and watched her credit be co-opted. Yet she responded not by quitting, but by manually making 3 million more observations, grinding through decades of obscurity, raising a family in an observatory during a world war, and ultimately tearing down the institutional barriers of Harvard University to become its first female department chair.
It is a legacy of unparalleled scientific brilliance, matched only by unyielding personal resilience. She fundamentally changed not just what we know about the physical makeup of the stars, but who is culturally permitted to study them.
I want to leave you, the listener, with one final thought. The next time you walk outside on a clear night and look up at the stars, knowing now that 98% of the observable matter you are looking at is a massive, glowing ocean of hydrogen and helium, ask yourself this: what other profound truths about our universe are currently sitting on a desk somewhere, being dismissed as spurious simply because they don't match the comfortable dogma of the day?